Okay, hi everyone. So for my discussion video, I chose to do number 11, which is covering mechanisms. Define and identify nucleophiles and electrophiles and show curved arrow notation to change reactants to products. So first off, just looking at the definition of what is a nucleophile, what is an electrophile. A nucleophile is a nucleus-loving species. These are species that donate an electron pair to form a new bond, and these are typically negatively charged, or they have a lone pair of electrons. For example, some of these could be like hydroxide ions, water, and ammonia, so like OH negative, H2O, and then NH3. And think of these as like a magnet for positive charges. So they're electron rich and they're nucleus loving, and they're able to donate those electrons because they have a pair available to be donated. And then for the electrophiles, these are electron loving species. These are species that accept an electron pair to form a new bond, and they typically have a positive charge or a partial positive charge. So, for example, some of those could be like CH3 plus, H plus, so just regular hydrogen ions, Fe3 plus, anything that's usually positively charged. So these are electrophiles are electron deficient, which means they love to receive electrons, and they accept those electron pairs to form bonds. So talking a little bit about the curved arrow notation and what that looks like for reactions. So in reaction mechanisms, the curved arrows are used to show electron movement. The arrow starts from the electron donor, the nucleophile, and then flows and points to the electron acceptor, which is the electrophile. So for example, just keep in mind that these arrows represent the direction of electron flow. So just looking at a few examples here, excuse the drawing, it's not the best, but you can see just here some examples of just defining a nucleophile, what those might be, some examples of different molecules, same with electrophiles, and just some quick examples of simple examples to show these curved arrow notation. So here we have the hydroxide ion, and these this lone pair of electrons is able to move and be donated to the CH3 plus. So we have the nucleophile and the electrophile, and then this is the resulting result of that donation. So then here again we have a negative fluoride ion, which is very electron rich, reacting with a BF3, and so these lone pairs will move to the boron, and then it accepts those and has